All right, in case you didn't have a chance on that other video to kind of look things over, here are our answers. This is our sample space. Getting a 6, there's only one of those in there. Not getting a 6, notice that that would be everything except this, so that would be 5 of them. Getting a 1 or a 2, that could be either of these situations, so that would be 2 out of 6, which reduces to a third. And not getting a 1 or a 2 is everything that isn't here, so that would be all of these. So that's your 4 over 6, which reduces to 2 over 3. So now we're going to move on. This is sort of leading us to what we're going to call complementary events, which is something that's good to know when you're doing probability. And that you try 5, probability of getting a 6 and probability of not getting a 6 together was equal to 1. So if I go back and look here, probability of getting a 6, probability of not getting a 6, and if I add those two together, a 6th plus 5/6 is 6 over 6, which is equal to 1. And the same thing happened here, getting a 1 or a 2, and the probability of not getting a 1 or a 2. If we look back, I would take getting a 1 or a 2, not getting a 1 or a 2. If I add those two events together, I get 3 over 3, which is also equal to 1. So what we've just looked at and kind of discovered is what complementary events are, and the sort of, if you want to write down some definition of that, exactly one event must occur. It's impossible for both events to occur simultaneously, so you cannot be a 1 or a 2 and also simultaneously not be a 1 or a 2. And the mathematical outcome of that is if you have an event and you have its complement, so this little tick mark up here means the complement of A. So those two things together added up have to equal 1. And if we do a little algebra, if I were to subtract either of these, I could, to kind of get it on its own. So if I wanted to find the complement, so A not occurring is the same as having that tick mark up there, that dash. This is the complement of A, is 1 minus the probability of A happening. So the complements add up to 1, so either of these two individually. So I could also talk about the probability of any event itself happening is 1 minus its complement happening. So this is a quick way to make some calculations in probability. If you know the probability of an event happening, you can quickly determine the probability that it doesn't happen by doing a quick subtraction from 1. So again, I somehow messed up the video screen on this, so I'll kind of show you what this problem is. We're going to use a table, a tree, or a grid to illustrate the sample space for tossing a coin and rolling a die simultaneously, and then determine each of these probabilities. So tossing a head, getting a tail and a 5, getting a tail or a 5. So I made a table, but this really is the same. You could quickly do this with like one of those grids if you wanted to, with your 1, 2, 3, 4, 5, 6, and your head, tail. Oops. And I just did it this direction because I had room over here. But if I want to find the probability of tossing a head, and I just look at this, first off, there's 2, 4, 6, 8, 10. There are 12 outcomes. So the probability of tossing a head, the head is in all of these on the top. And if I use this, it would be in all of these up here. I'd put little dots in all of these. So that is 6 out of 12, or a half. Getting a head and, a tail and a 5. So that means they have to happen at the exact same time. So if I look down here for when I have a tail and a 5, it's right here. And that's the only one that has both of them happening simultaneously, so that'd be 1 out of 12. And if I were to do it over here, if I wanted a tail and a 5, it would be that 1 dot out of the 12 that would be here, and I kind of just made it a little bigger and brighter, but it would be that 1 out of 12. All right, and so I'm going to kind of switch colors. A tail or a 5 means it could be a tail or it could be a 5. So all of these have tails. And these two have 5s, so if I add all of those up, it would be, there's 6 down here, and that one right there would be 7 out of 12. And if I were to do it here, a tail or a 5, and I just color these all in with red, again, I could add those all up and I'd have 7 out of 12. All right, you're going to do the same thing, but you're going to do it with this spinner, which has equal shapes on it. Again, 2 square spinners, 1, 2, 3, 4, twirled simultaneously. You have 2 of these. I know there's a picture of one, but you have 2 of them. You can make a grid, a table, or a tree for the possible outcomes to determine your probabilities. So pause it, try it. Again, you have 2 of those, not just 1. All right, so I made a tree, and here are tables to indicate what your outcomes are. So this is where a tree can be completely annoying and difficult. But if I wanted to get a 3 with each spinner, that means I have to get a 3 first, and then I have to get a 3 again. So that only happens on this little tree branch here. So that's 1 outcome. And you'll notice if I count up all, I didn't list my sample space over here, which I should have, but there's 16 possible outcomes and only 1 of them has a 3 in both. Using the table, a 3 and a 1, I needed both of those things to occur simultaneously. And so you'll notice that's 2 out of the 16 in my sample space. That reduces to an 1/8. And if I just want to get an even result for each spinner, that means both spinners have to land on either 2 or 4. So again, I use this and I can count up that happened on 4 of them, and so that'd be 4 out of 16 or a quarter. All right, this is using the grid instead, and just kind of verifying those same results. So kind of see all 3 methods: a tree, a table, and a grid. So now we're going to look at the probability of getting marbles out of a box, and you can kind of see, I can scooch this to this side a little bit, you can see what's going on. So we've got boxes, 2 boxes of marbles, box X and box Y, and you can see some are green and blue, some are red and white, and we want to find the probability of getting a blue marble from X and a red marble from Y. So you're supposed to just take a guess at what that probability would be first. So take a guess, just picking 1 marble out of here, it's green. Oh, sorry, 1 marble out of here, it's blue, and then picking 1 out of here and it's red. What do you think the chances of that happening in that combination? So let's look at our answers with the grid. Again, if we make the grid, notice that we have 1, 2, 3, 4 by 4, so we have 16 outcomes, and 6 of them would result in that particular outcome I'm interested in. If I make the table, I have 6 outcomes. And I'm going to come back to this tree because I was interested in getting a blue marble and then a red marble. So that would be this path right here, blue and red. That's the only one that I would be interested in. So we'll look at these numbers that I've written over here in a minute. Basically, I looked up here, green. To get a green, there's a 2 out of 4 chance, and I just reduced it. Blue, just grabbing a blue would be 2 out of 4, and I reduced it. And the same here, red would be 3 out of 4. And getting a white would be 1 out of 4. So I listed the probabilities of each event as it went along the tree branch. So basically the probability of getting a blue and a red is 6 out of 16, which reduces to 3/8. And there's our answer so that you can believe me, it's true. And again, we're going to come back to this word "and" makes a difference in this calculation. But again, let's say I'm tired of drawing these tables and diagrams, so let's look at a better way. And we're going to talk about things being independent. It's a pretty big deal. And independence occur in this. I'm going to move this down because you want this definition. Events are independent if the occurrence of either of them does not affect the probability of the other. So independence is what it always means. If things are independent, they don't impact each other. Same in probability. And that's what independent events are. So in our little picture here, me picking a blue one out of here has no impact on whether what color I choose out of here. So these 2 events do not impact each other at all. So this is the individual probabilities I was talking about before. Pulling a blue marble from here is a 2 out of 4 chance. A red marble was 3 out of 4. And because they are independent, and this word "and" in here means multiply. So if events are independent and I want the word "and" in here, I can multiply those 2 individual probabilities, and notice it equals the same thing that I had. And notice on my tree branch, if I take my blue outcome and my red outcome, and that's the one I'm interested in, and I do 1/2 times 3/4, which are the individual probabilities as I move, and this is happening after the blue one, I get 3 out of 8 which is the same thing that I was hoping for. So this is in your note sheet. If events are independent, and I'm asking you to find the probability of one happening and another event happening, and means I can multiply. And this continues if I am trying to do that with 3 events. So if you had a tree diagram with 3 branches, you just multiply along your branches and boom, 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 you get your answer. All right, so compound events, example 7, a coin and a die are tossed simultaneously. So apparently you have a die in one hand, a coin in the other, and same exact time, boom, you shoot them. I want the probability of getting a head and a 3. I don't want to use a grid, so I'm going to start using kind of fancy notation, the probability of getting a head and a 3. And later we'll use a different notation for this word and. It's going to be this kind of horseshoe looking thing, but it's going to go that direction. That means I can, again, flipping a coin and rolling a die, independent. They do not impact each other. The die is not controlling the coin or vice versa. So I can just find the probability of getting a head times the probability of getting a 3. I already know the probability of getting a head is 1 out of 2 when I flip, and we've looked at this. If I have 6 sides to a fair die, 3 only is on 1 of the 6 sides, so I would have a 1, I don't know why I wrote 3 down there, 1 out of 6 chance. Let me make this official because that is just too messy to count. All right, and that means I'd have a 1 in 12 shot of flipping ahead and the die rolling up on ending up on a 3. So that's my probability of that happening without using a grid, recognizing that this is the word and that these 2 events are independent. So boom, there I go, I can multiply. So you're going to try this. I'm going to move this down so you can see this. This is a very interesting example. A couple wants to have 4 kids, none of whom will be adopted, and they will be disappointed if the children are not born in this very particular order. Boy, girl, boy, girl. Like they like patterns. Determine the probability that they will be happy and then unhappy. So it's going to kind of put a couple things together. So basically they want to have a boy and then a girl and then a boy and then a girl. And I will tell you, we're going to use the idea theoretically that there's a 50-50 shot of having either gender. So we want boy, girl, boy, girl. So now we know the probability of having a boy and a probability of having a girl. We're going to assume that they're both 50%. And also, just so you're aware, the gender of these children in order are independent. So once you have a child, the gender of the next child doesn't remember what the gender of the first child was, if that makes sense. So these events should be considered independent. So give this thing a go, pause it, try it. All right, so you would be happy if you got the events in this order. We're allowed to multiply them because it's an and each one is a half. So if I multiply a half times a half times a half times a half, there is a 1 in 16 shot that they would be happy. And so unhappy is the complement of happy. So if this was probability of happy, this would be not happy. And we know that that is 1 minus the probability of happy. So I can take the 1/16, take it away from the 1. And so there is only a 1 in 16 chance, excuse me, that they're going to be pleased with their outcome. So 15 out of 16 that they're going to be displeased. So you can imagine the probability of them being happy is just not good. It's not good at all. And now we're going to move into dependent events. We've been talking about independent, so dependent is kind of the opposite of that. And events are dependent if the occurrence of one event does affect the occurrence of the other event. So this is the exact opposite. So now they actually impact each other. So one does have something to do with the other one. So if I go back to our the same example we were doing before with the marbles, you see you've got the exact same bin in there, except for that instead of being in separate boxes, now they're all in one box. It's all in the same bin. It's crazy. Now I'm going to take one marble out of the box and then a second marble out of the box. And what is the chance that the second marble is red? Well, it depends, because the first marble is red, it'd be 2 out of 7. But if the first marble wasn't red, it'd be 3 out of 7. So here's example 8.